Welcome to Softly Curious. Tonight, we begin at the moment before architecture had a name. Before blueprints, before columns, before cities rose in stone and glass, it was a quieter decision to stay, to shape the ground instead of simply walking across it. Architecture did not begin with decoration. It began with intention. Long before written language, people gathered in places that mattered. One of the clearest signs of this early intention stands on a hill in southeastern Anatolia. At Göbekli Tepe, massive T-shaped stone pillars were arranged in circular enclosures more than 11,000 years ago. These structures were not houses. There are no hearths, no signs of domestic life. Instead, carved animals move across the surfaces of the pillars, suggesting ritual and shared belief. The sequence is striking. Monumental construction appears before permanent settlement. In other words, the impulse to build for meaning may have preceded the impulse to build for shelter. Architecture, at its origin, was not only protection from weather. It was a way to mark significance. Further south, near a fertile oasis in the Jordan Valley, another early structure still rises from the earth. The Jericho Tower, built around 8000 BCE, is a massive stone construction attached to what may have been one of the earliest known city walls. It stands roughly 8 meters tall, with an internal staircase carefully constructed from stone. Whether defensive, ceremonial, or symbolic, its scale suggests coordination. It required planning, labor organization, and knowledge of weight and stability. Even at this early stage, architecture demanded cooperation. A wall is never a single person's decision. It is a collective agreement about boundaries. At Çatalhöyük in central Anatolia, dating to around 7500 BCE, a different architectural idea appears. The houses were tightly clustered, built wall to wall, with no streets between them. Entry was not through doors at ground level, but through openings in the roof. Residents climbed down ladders into their homes. This design minimized external access and likely increased security. The roofscape functioned as circulation space, almost like a horizontal village square. Here, architecture begins to define movement patterns. How one enters a home shapes how one experiences privacy and community. These early settlements relied heavily on mud brick. Neolithic builders developed techniques for forming clay mixed with straw, shaping it into blocks and drying it in the sun. Mud brick has limits. It cannot span large distances without support. It erodes with rain, yet it offers insulation and can be repaired easily. The material shaped the architecture. Walls were thick. Openings were small. Buildings were often rebuilt atop older foundations, creating layered mounds over centuries. In places along the Nile and the Euphrates, entire early cities rose from this earth-based technology. Material and climate formed a quiet partnership. Elsewhere, in Western Europe, massive stones were arranged in deliberate patterns. The megalithic culture left behind structures that continue to raise questions. At Stonehenge, stones were aligned with celestial events, including the summer solstice sunrise. This alignment required observation of the sky over long periods. The stones were not randomly placed. Their positions indicate an understanding of orientation and horizon markers. Architecture here becomes a frame for time itself. It anchors human life to astronomical cycles. Even deeper in time, before constructed walls, humans marked space inside natural enclosures. The cave paintings at Lascaux in present-day France are often discussed as art, but they also reveal spatial awareness. The placement of animals within the cave chambers follows contours of the rock. Certain chambers appear to have been used repeatedly. Space was chosen not accidental. The cave became more than shelter. It became a designed interior, shaped by image and movement. As structures grew more complex, a simple structural principle began to appear repeatedly. The post and lintel system, sometimes called the trebiated system, involves two vertical supports carrying a horizontal beam. It seems elementary, yet it represents a leap in abstraction. A horizontal span can bridge space. Openings can be created intentionally. This system appears in early stone constructions and later in refined forms across many cultures. Its logic is direct. Gravity presses downward. Vertical supports transfer load to the ground. Architecture begins to engage physics in visible form. Stone stacking techniques also evolved. Dry stone walls, built without mortar, rely on careful placement and gravity. The weight of each stone stabilizes the one below. Irregular shapes are chosen deliberately to interlock. This method appears in early settlements and later in advanced forms, such as in the stone terraces of various ancient cultures. It reflects an understanding that stability can be achieved without binding agents if geometry is respected. Wood, though less likely to survive in the archaeological record, played a significant role. Early timber frames provided flexible structural systems. Wooden posts embedded in the ground supported roofs of branches and thatch. Timber allowed lighter spans and faster construction. In forested regions, it became the primary building material. While stone suggests permanence, wood suggests adaptability. The choice between them was rarely aesthetic. It was ecological. In river valleys, such as those of the Nile and the Tigris-Euphrates, mud brick cities expanded in response to agricultural surplus. Irrigation systems enabled population growth, and population growth demanded organization. Urban clusters began to form, with defined zones for storage, ritual, and dwelling. The material remained humble, but the planning became more deliberate. Architecture began to operate at the scale of settlement rather than individual shelter. Climate exerted quiet pressure on all these forms. In hot, arid regions, thick walls moderated temperature. Small windows reduced heat gain. In colder climates, structures were often partially embedded in the ground for insulation. Roof angles varied according to rainfall. Flat roofs suited dry regions. Steeper roofs shed snow and water. The plan of a building often mirrors the sky above it. Architecture listens to weather. Not all early architecture was sedentary. Nomadic cultures developed portable systems that balanced stability with mobility. The Central Asian yurt, with its circular plan and collapsible wooden lattice, can be assembled and dismantled efficiently. Its form distributes structural forces evenly across the frame. Bedouin tents, woven from goat hair, expand when wet and contract when dry, adjusting to environmental conditions. These structures demonstrate that architecture is not defined by permanence. It is defined by organization of space. The concept of a wall marks a turning point. A wall separates inside from outside. It establishes ownership, safety, and sometimes exclusion. Early walls likely served multiple functions: defense against animals, protection from wind, demarcation of social territory. Once walls exist, doors follow. Once doors exist, thresholds acquire meaning. Architecture begins to choreograph entry. Alongside the wall emerges the idea of shared space. Archaeological evidence suggests that early settlements included open areas used for gathering. These proto-squares functioned as communal zones for exchange and ritual. Even without formal paving, repeated use defined them. The space between buildings gained importance. Architecture is not only about enclosure, it is also about what is left open. Topography influenced settlement patterns in profound ways. Villages were often placed on elevated ground for defense and drainage. Riverbanks offered fertility but risked flooding. Hillsides required terracing. Builders responded to slope by carving or reinforcing terrain. In mountainous regions, structures were integrated into the landscape rather than imposed upon it. The land was not a blank canvas. It was an active participant. Over centuries, Early building knowledge spread not through books, but through repetition. Techniques improved quietly. Walls became thicker where wind demanded it. Foundations were laid more carefully where soil shifted. Builders learned from failure as much as from success. Architecture evolved through observation, not theory. Each adjustment, however small, added to a growing body of shared understanding. Even in these early constructions, patterns begin to appear. Structures are aligned with cardinal directions. Some are oriented toward sunrise or seasonal events. Circular plans emerge in both ritual spaces and dwellings, suggesting an intuitive preference for enclosure without corners. Proportions often relate subtly to the human body, to standing height and reach. These choices were not random. They reflect consistent spatial reasoning across distant regions. What stands out is not the scale of these early structures, but their intention. At Göbekli Tepe, pillars were placed in deliberate arrangement. In Cataluyuk, access through rooftops shaped daily life. The tower at Jericho required organized labor beyond immediate necessity. Architecture at this stage was already more than shelter. It was a conscious shaping of environment, guided by foresight, cooperation, and a growing sense of place. As settlements stabilized and knowledge accumulated, architecture began to move from instinct to system. In ancient Egypt, geometry became a structural language. The pyramids on the Giza Plateau were not only massive tombs, but precise geometric compositions. Their square bases align closely with cardinal directions, and their slopes reflect consistent angular calculations. The pyramid form distributes weight downward and outward, stabilizing enormous stone mass through simple gravitational logic. Earlier in Egyptian history, the step pyramid at Saqqara marked a turning point. Designed under the supervision of Imhotep, it transformed the traditional flat mastaba tomb into a stacked, ascending form. This shift was conceptual as well as structural. Architecture began to express hierarchy in vertical terms. The structure was no longer only protective. It was symbolic of ascent. In Mesopotamia, the ziggurat introduced a different architectural vocabulary. The ziggurat of Ur rose in step terraces, each level diminishing in scale. Built from mud brick with baked brick facing, it elevated sacred space above the surrounding city. The platform system emphasized separation between earthly and divine realms. The structure's geometry was deliberate, its mass carefully staged in layers. In ancient Greece, refinement replaced monumentality. The Parthenon in Athens demonstrates a sophisticated understanding of proportion and optical correction. Columns are subtly curved, and the stylobate gently rises at the center to counter visual distortion. Ratios between column height, spacing, and entablature create harmony. The building is a study in measured balance rather than sheer scale. Roman architecture expanded these principles into theory. The architect Vitruvius articulated three core values: firmitas, utilitas, and venustus, strength, function, and beauty. This triad framed architecture as both engineering and art. Roman builders applied these principles across an empire, combining structural innovation with systematic planning. The Roman arch became one of the most transformative structural devices in history. By transferring loads outward and downward through curved compression, arches allowed wider spans and more durable construction. The Colosseum employs a layered system of arches and vaults, creating circulation corridors and tiered seating within a stable framework. Its exterior arcades are not merely decorative. They express the internal structure. The Pantheon represents another leap. Its vast concrete dome, still the largest unreinforced concrete dome in the world, rests on a thick cylindrical drum. The oculus at its center reduces weight and allows light to enter as a controlled beam. Roman concrete, made with volcanic ash, hardened underwater and provided unprecedented flexibility. The dome's thickness decreases toward the top, subtly reducing stress. In East Asia, structural innovation took a different path. The Chinese dugong system interlocking wooden brackets allowed roofs to extend outward dramatically while distributing weight efficiently. These layered brackets absorb seismic movement and support sweeping eaves. Instead of relying on rigid mass, the system uses flexibility and joint precision to maintain stability. In the Andes, Machu Picchu demonstrates mastery of stone without mortar. Stones were cut with such precision that joints remain tight centuries later. The structures respond to steep terrain through terracing and stepped foundations. Walls often incline slightly inward, increasing resistance to seismic forces. Architecture here adapts to both gravity and geology. In the desert landscape of Jordan, the city of Petra was carved directly into sandstone cliffs. Rather than assembling blocks, Nabatean builders subtracted material. Facades such as Al-Khazna were sculpted from rock faces, blending Hellenistic decorative language with local tradition. The architecture merges geology and design. Roman infrastructure extended beyond monumental buildings. The Pont du Gard aqueduct in southern France carried water across valleys through stacked arches of carefully cut stone. Roman roads, laid in layered stone foundations, formed grid patterns across conquered territories. Standardized planning facilitated trade, movement, and military control. Further east, the cities of the Indus Valley Civilization reveal advanced urban planning. Settlements such as Mohenjo-Daro were organized on grid systems with standardized brick sizes and integrated drainage networks. In Mesoamerica, Maya pyramids rose as stepped platforms supporting temples, often aligned with celestial events. In ancient Japan, temple architecture developed modular proportions based on standardized bay spacing, allowing structures to be dismantled and rebuilt with consistency. Across continents, architectural systems became deliberate, repeatable, and deeply embedded in cultural logic. Architecture is often described through style, symbolism, or historical period. Yet beneath every facade lies a quieter conversation between forces. Buildings stand because materials respond in predictable ways to pressure. Before ornament, before proportion, there is physics. The first distinction builders learned, even without formal language, was the difference between compression and tension. Compression pushes inward, squeezing material together. Tension pulls outward, stretching it apart. Stone performs well under compression. Rope performs well under tension. Early architecture relied heavily on materials that could endure being pressed downward by weight. When a stone column supports a beam, gravity compresses the stone. If the same stone were pulled apart, it would fracture. Structural logic begins with respecting these limits. Stone's resistance to compression explains its dominance in ancient monumental architecture. Limestone, granite, and sandstone can withstand immense downward force without deforming. Egyptian pyramids depend almost entirely on this property. Their mass is stable because gravity pushes every block downward into the one beneath it. The shape itself assists stability. Angled sides direct weight toward the ground. There is no need for internal steel reinforcement. The geometry collaborates with gravity. Wood behaves differently. Its internal fiber structure gives it remarkable tensile strength relative to its weight. A wooden beam can span a distance and resist bending because its fibers act like bundled threads. Under load, the upper fibers compress while the lower fibers stretch. As civilizations expanded, builders experimented with composite materials. Roman engineers developed opus caementitium, a form of concrete made by mixing lime mortar with volcanic ash and aggregates. Unlike simple mortar, this material could harden underwater and form monolithic masses. Roman concrete did not rely solely on stacked blocks. It allowed walls and domes to be poured into shape. The result was a shift from assembled architecture to cast architecture. Structure became more fluid. Brick introduced another layer of refinement. Unlike irregular stone, brick can be standardized. Uniform size allows predictable bonding patterns. Courses align. Openings can be calculated more precisely. In Mesopotamia and later in Roman territories, brick became a reliable modular unit. Its repeatability made large-scale construction more efficient. Standardization, even in ancient times, was a structural advantage. The arch marked a profound understanding of compression. Instead of placing a horizontal beam across two supports, builders arranged wedge-shaped stones in a curve. Each stone presses against its neighbor. The load travels along the curve and disperses into the supports. The keystone at the top locks the system together. An arch cannot stand until complete, but once assembled, it channels force efficiently. It transforms downward weight into lateral thrust. From the arch emerged the vault. A barrel vault extends the arch into 3 dimensions, forming a continuous tunnel-like ceiling. Roman baths and basilicas demonstrate this technique. By repeating the arch along a length, large interior spaces could be covered without timber roofs. Stone and concrete, working in compression, created enclosed volumes that felt expansive and stable. Medieval builders refined this system further in Gothic cathedrals. The flying buttress addressed a specific problem: the lateral thrust produced by tall vaulted ceilings. Instead of thickening walls indefinitely, architects redirected outward forces through arch supports to external piers. The wall became thinner, allowing large stained glass windows. Structure and light entered into negotiation. The buttress is not decorative. It is a visible diagram of force. In parallel, different cultures explored shell structures. A shell relies on curvature to distribute loads across its surface. Even thin materials can become strong when shaped into curves. Early domes and later thin concrete shells illustrate this principle. The form itself becomes structural reinforcement. A curved surface resists deformation more effectively than a flat one of similar thickness. Column orders in ancient Greece represent another structural and aesthetic synthesis. The Doric order emphasizes solidity with thick columns and simple capitals. The Ionic order introduces slender proportions and volutes. The Corinthian order becomes more elaborate. While often discussed stylistically, these orders also encode structural ratios. Column height relative to diameter affects stability. Proportion becomes a form of engineering discipline. Load-bearing wall construction dominated for centuries. In this system, walls carry the weight of floors and roofs. Openings must remain limited to preserve integrity. The thickness of the wall often indicates the height it can support. Medieval castles and early urban buildings relied on this principle. Stability required mass. The transition towards skeletal systems marked a conceptual shift. Instead of walls carrying weight, internal frames could do so. Timber framing anticipated this approach. Later, metal structures formalized it. When a building's load transfers through a defined framework of columns and beams, walls can become lighter enclosures rather than primary supports. This separation between structure and skin altered architectural possibilities. The dome illustrates structural geometry in its most concentrated form. A dome channels compressive forces downward and outward along its curve. The circular base distributes these forces evenly. Without reinforcement, a dome must be thick at its base and gradually thinner toward the apex. Roman engineers understood this, reducing material thickness as height increased. Geometry becomes structural intelligence. Stone cutting techniques evolved in response to structural demand. Quarrying required understanding fraction lines. Masons shaped blocks to interlock precisely. In Inca architecture, stones were cut with angled faces to resist seismic movement. In European cathedrals, ashlar masonry achieved tight joints that minimized shifting. Precision reduces vulnerability. Regions prone to earthquakes developed distinct structural adaptations. In Japan, wooden temples use flexible joinery that allows movement without collapse. Timber frames absorb energy through joints rather than rigidly resisting it. In parts of the Mediterranean, walls incorporated wooden bands to add flexibility within stone construction. Structural logic adapts to geological conditions. Material choice is rarely arbitrary. In arid regions, thick adobe walls moderate temperature. In forested climates, timber predominates. In volcanic areas, basalt and tuff become building stone. Structural systems evolve in dialogue with local resources. Technology expands options, but environment sets constraints. Understanding structural logic also means acknowledging failure. Collapsed arches exposed mismanaged thrust. Cracked domes revealed uneven force distribution. Builders did not advance through theory alone, but through correction. Each structural refinement carries the memory of earlier mistakes quietly resolved. Long before steel frames appeared, architects had already mastered compression, span, and curvature. The dome of the Pantheon, Gothic vaulting systems, and enduring stone bridges show how deeply material behavior was understood. These structures stand not because they are heavy, but because their geometry guides force where it can be safely absorbed. Structural logic rarely calls attention to itself. It lives in wall thickness, joint precision, and subtle curvature. Masonry communicates stability through mass. Timber expresses lightness through span. Across centuries, architecture has balanced compression and tension with quiet discipline. Form follows force, even when it does not announce it. The 19th century transformed structural possibility through metallurgy. The Bessemer process, developed by Henry Bessemer in the 1850s, made steel production faster and significantly cheaper. By blowing air through molten iron to remove impurities, large quantities of strong, relatively uniform steel could be produced at industrial scale. Steel combined high tensile strength with compressive capacity, allowing structures to move beyond the limitations of stone and unreinforced masonry. For the first time, height was no longer constrained primarily by wall thickness. The engineering of the Eiffel Tower in 1889 demonstrated what this new material could achieve. Designed by Gustav Eiffel and his team, the iron lattice structure distributes wind loads through a network of interconnected members rather than relying on solid mass. Its open framework reduces resistance to wind while maintaining stability. The tower's curved profile was calculated mathematically to respond to aerodynamic forces. Structure became visibly analytical. In the United States, the Chicago School embraced the steel frame as the backbone of urban growth. After the Great Chicago Fire of 1871, rebuilding required fire-resistant and structurally efficient systems. Steel skeletons allowed buildings to rise vertically without excessively thick lower walls. Columns and beams formed internal frameworks that carried loads independently of exterior walls. This separation made new architectural typologies possible. The elevator accelerated this vertical transformation. Although structural steel enabled height, it was the safe passenger elevator refined by Elisha Otis that made tall buildings practical for daily use. Without reliable vertical transportation, upper floors would remain undesirable. Once elevators became trusted systems, the economic value of height increased dramatically. The skyscraper became both an engineering and social invention. As structural frames evolved, exterior walls changed role. The curtain wall system detached facade from structural responsibility. Instead of bearing weight, the exterior became a lightweight envelope, often composed of glass and metal panels. This shift allowed extensive glazing and flexible interior layouts. The facade could now prioritize light and appearance rather than structural mass. Parallel to steel development, reinforced concrete expanded structural versatility. The Hennebeek system, patented by Francois Hennebeek in the late 19th century, embedded steel reinforcement within concrete to resist tensile forces. Concrete could handle compression, while steel bars absorbed tension. This composite logic allowed slabs, beams, and columns to act as integrated systems. Reinforced concrete reshaped bridges, housing, and industrial architecture across Europe. In early 20th century Germany, the Bauhaus movement reframed structural clarity as aesthetic principle. Functionality and material honesty were prioritized over ornament. Structural systems were not concealed, they were expressed. The alignment between purpose and form became central. Architecture was expected to reflect industrial efficiency and rational construction. Le Corbusier articulated 5 points of modern architecture that further redefined structural logic. Pilates lifting the building from the ground, free plan enabled by structural frames, free facade independent of structure, horizontal ribbon windows, and roof gardens. These principles relied on reinforced concrete frames. Once structure was concentrated in columns and slabs, interior walls no longer had to carry loads. Space became fluid. Across the Atlantic, Frank Lloyd Wright explored the cantilever, a structural gesture extending beyond its support without visible bracing. In projects like Falling Water, horizontal slabs project outward over a waterfall. Reinforced concrete carries bending forces through internal steel reinforcement. The cantilever redefines equilibrium, allowing space to extend dramatically while remaining balanced. Mid-century experimentation expanded structural imagination further. Buckminster Fuller's geodesic dome used a network of triangles to distribute stress evenly across a spherical surface. The triangular geometry provides inherent stability, enabling large spans with minimal material. The dome's efficiency lies in its distribution of force through interconnected elements rather than heavy mass. Late 20th and early 21st century architecture embraced computational design. Zaha Hadid employed parametric modeling to generate fluid, continuous forms shaped by algorithms. Structure and surface intertwine, often relying on advanced steel and concrete systems to support sweeping curves. Similarly, Santiago Calatrava developed biomorphic structures inspired by skeletal and muscular systems. His designs often expose structural components, emphasizing motion and tension as visual themes. Contemporary engineering continues to refine material systems. Tensegrity structures balance compression and tension through isolated struts held in place by continuous cables. Stability emerges from equilibrium rather than mass. 3D printed houses use robotic extrusion of concrete or composite materials, reducing waste and construction time. Advanced materials such as carbon fiber and new composites provide high strength-to-weight ratios, enabling lighter yet resilient structures. Modern structural logic increasingly blends digital calculation with material innovation, continuing the long dialogue between force and form. Some spaces are built not only to contain people, but to orient them. Sacred architecture does not simply provide shelter for ritual. It frames belief, directs movement, and aligns the human body with something beyond itself. Across cultures and centuries, builders have used geometry, light, height, and axis to give form to devotion. In these spaces, structure becomes cosmology made visible. In Barcelona, the Sagrada Familia, designed by Antoni Gaudí, rises like a forest translated into stone. Gaudí rejected rigid historical imitation and instead studied natural geometry. Columns branch like trees, distributing weight through angled supports that echo organic growth. The interior is calibrated to light. Colored glass filters sunlight into shifting tones that change throughout the day. Gaudí understood that vertical ascent could suggest spiritual aspiration, yet he grounded his forms in precise structural calculation. Hyperbolic paraboloids and catenary arches govern the weight distribution. Faith and mathematics coexist without contradiction. Centuries earlier, the builders of Chartres Cathedral in France mastered another language of light. Its stained glass windows are not merely decorative surfaces, but theological narratives rendered in color. The deep blues and reds modulate interior illumination, transforming sunlight into filtered radiance. The height of the nave and the pointed arches draw the eye upward, but it is the glass that shapes atmosphere. Light becomes a medium of instruction. The building is not only entered physically, it is absorbed visually. The dome of Hagia Sophia in Istanbul marked a structural and symbolic revolution when it was completed in 537 CE. Its vast central dome appears to float above a ring of windows at its base. The architects, Anthemius of Tralles and Isidore of Miletus, used pendentives to transition from a square base to a circular dome. This innovation allowed a unified interior volume unprecedented at the time. The dome's height and the diffuse light entering from below create the impression of suspension. Space feels weightless, even though it rests on massive piers. In Cambodia, Angkor Wat was conceived as a cosmic diagram. Its central tower represents Mount Meru, the mythological axis of the Hindu universe. Surrounding galleries and moats correspond to cosmic oceans and mountain ranges. The plan is axial and symmetrical, guiding movement toward the elevated center. Orientation is deliberate. Angkor Wat faces west, a direction associated with Vishnu and with funerary symbolism. Architecture becomes a map of belief, scaled to landscape. In Mecca, the Kaaba anchors Islamic worship through orientation. Muslims across the world turn toward it during prayer. The ritual of tawaf involves circumambulating the cubic structure 7 times in a counterclockwise direction. The geometry is simple, but the act of circling establishes a spatial rhythm shared by millions. The sacred is not expressed through monumental height, but through unified direction. Orientation itself becomes architecture's central gesture. In Indonesia, Borobudur unfolds as a 3-dimensional mandala. Built in the 9th century, the structure consists of ascending terraces that transition from square to circular platforms. Relief panels narrate Buddhist teachings as pilgrims move upward. The path is not linear but circumambulatory, requiring repeated circulation around each level before ascent. The architecture embodies spiritual progression. Geometry here guides contemplation. Deep in the Guatemalan rainforest, the temples of Tikal rise steeply above the canopy. These stepped pyramids were aligned with astronomical events and dynastic symbolism. Their height elevates ritual above the surrounding environment. The steep staircases reinforce vertical hierarchy. The summit platforms frame sky rather than landscape. Architecture in Tikal acts as both observatory and throne. In Japan, Shinto shrines express sacred continuity through renewal rather than permanence. At the Ai's Grand Shrine, buildings are dismantled and reconstructed approximately every 20 years. The materials remain wood, and techniques remain traditional. The practice preserves craftsmanship while acknowledging impermanence. Sacred architecture here is cyclical. Its meaning lies not in endurance of material, but in endurance of ritual. The Gothic ascent of Notre Dame in Paris continues the medieval ambition to dissolve stone into light. Flying buttresses redirect structural thrust outward, allowing interior walls to open into vast stained glass compositions. Vertical lines emphasize elevation. The building's proportions encourage upward gaze. In Gothic architecture, height becomes devotion translated into structure. Long before medieval cathedrals, Stonehenge aligned massive stones with solar events. The heel stone frames the sunrise at the summer solstice. The circular arrangement suggests cyclical time. Though constructed in stages over centuries, its orientation reflects sustained observation of the sky. The stones mark seasonal transition. Architecture here binds human ceremony to astronomical precision. In ancient Mesopotamia, ziggurats such as those in Ur functioned as symbolic mountains rising from flat plains. Each ascending level separated sacred space from ordinary ground. The form reinforced hierarchical cosmology. Access was restricted. Height signified proximity to the divine. The step geometry translated spiritual ascent into physical movement. Across the ocean, the Templo Mayor in Tenochtitlan embodied Aztec cosmology. Dual temples crowned the pyramid, dedicated to Huitzilopochtli and Tlaloc. The structure aligned with solar cycles and ritual calendars. The pyramid served as both ceremonial stage and cosmic diagram. Architecture and sacrifice intersected at its summit, reinforcing political and spiritual authority. The Temple Mount in Jerusalem concentrates layers of sacred association. Across millennia, it has held the first and second Jewish temples, later the Dome of the Rock and Al-Aqsa Mosque. The elevated platform defines sacred territory. Its geometry creates a threshold between ordinary city and spiritual access. Few spaces carry such accumulated meaning within a defined perimeter. In the Andes, the alignment of Machu Picchu reveals a different sacred geometry. Structures are positioned in relation to surrounding peaks considered holy. The Intihuatana stone is aligned with solstice events. Rather than dominating landscape, the city integrates with it. Terraces, temples, and axes respond to mountain contours. Sacred orientation extends beyond walls into terrain. Buddhist stupas, found across South and Southeast Asia, encode cosmology through form. A hemispherical dome rises from a square base, often crowned by a spire representing the axis mundi. Circumambulation paths encourage ritual movement around the structure. The stupa is both relic container and symbolic universe. Its geometry simplifies complexity into a balanced whole. Across these diverse examples, sacred architecture demonstrates a consistent impulse to align built form with invisible order. Whether through light filtered by glass, domes suspended above open space, pyramids aligned with celestial bodies, or platforms marking holy ground, these structures guide perception. They create centers. They establish axes. They transform orientation into meaning. Sacred space is never random. It is measured and aligned to guide attention and shape meaning. Proportion, light, and orientation matter more than scale. Across cultures, builders use geometry and structure to connect earth with sky, turning walls, domes, and axes into expressions of belief. In these places, architecture becomes more than shelter. It becomes a quiet bridge between human ritual and a larger cosmic order. Sacred architecture does not only express belief, it also expresses power. Few examples demonstrate this more clearly than the Palace of Versailles, where scale, symmetry, and axial planning reinforce the authority of Louis XIV. Long corridors, controlled sightlines, and vast gardens extend the king's presence into landscape. Space becomes choreography. Movement through the palace subtly reinforces hierarchy. In Beijing, the Forbidden City operates through layered enclosure and strict axial alignment. Its north-south central axis organizes courtyards, halls, and gates in a sequence that reinforces imperial order. Access narrows as one approaches the inner sanctum. Architecture here structures authority spatially. The plan itself embodies political structure. The Kremlin in Moscow merges religious and defensive symbolism. Its fortified walls and towers define a protected core, while cathedrals within signal spiritual legitimacy. The red brick ramparts are not merely military. They communicate endurance. Architecture becomes both shield and statement. In the United States, the dome of the Capitol building draws from classical precedent to frame democracy within a recognizable architectural language. Its elevated position on Capitol Hill reinforces institutional gravity. Nearby, the Washington Monument rises in simple obelisk form, its height carefully proportioned to dominate the skyline without ornament. Verticality becomes memory rendered in stone. The 20th century revealed how architecture could be mobilized for ideological spectacle. Under Albert Speer, Nazi architecture emphasized overwhelming scale and rigid symmetry to project permanence. Monumental plans and vast parade grounds were designed to diminish the individual within collective mass. In fascist Italy, Mussolini's rationalist buildings adopted strict classical forms, presenting authority through stark geometry and disciplined repetition. Monumental squares amplify this psychological effect. Large open plazas, bordered by imposing facades, shape perception through scale. The individual crossing such a space becomes aware of proportion. Emptiness itself becomes an instrument. Architecture frames gathering, ceremony, and demonstration with spatial control. Earlier precedents also fused power and memory. The mausoleum of Halicarnassus, one of the 7 wonders of the ancient world, elevated a ruler's tomb into architectural grandeur. Its layered structure and sculptural program transformed burial into public statement. Centuries later, the Taj Mahal employed perfect symmetry and reflective pools to create an image of balance and eternal love. Its geometry communicates serenity through precision. In Washington, the Lincoln Memorial anchors a symbolic axis stretching across the National Mall. The seated statue faces the Capitol, creating a visual dialogue between branches of governance. The alignment organizes civic memory into spatial sequence. Visitors do not simply enter a building. They move along an intentional narrative path. Modern architecture sometimes counters monumentality with transparency. The glass dome added to the Reichstag in Berlin allows visitors to look down into the parliamentary chamber. The design symbolizes political openness. Structure here becomes metaphor without abandoning engineering logic. Memory architecture can also adopt restraint. Yad Vashem in Jerusalem cuts into the hillside, guiding visitors through angled corridors that compress and release space. The Hiroshima Peace Memorial, preserved in ruin, stands as absence rather than reconstruction. Meanwhile, minimalist contemporary worship spaces reduce ornament to emphasize silence and light. In these examples, power yields to reflection. Space shapes emotion quietly, proving that architecture's psychological force can emerge from stillness as much as from scale. A city is not only a collection of buildings. It is an agreement about order. Streets decide how bodies move. Walls define who belongs inside. Squares determine where voices gather. From the earliest settlements to modern capitals, urban planning has quietly shaped power, trade, ritual, and daily rhythm. One of the clearest early urban systems emerged in the Roman world. The Cardo Decumanus plan organized cities along 2 primary axes, the Cardo running north-south and the Decumanus running east-west. Their intersection typically marked the civic center. This grid was not decorative. It simplified military control, taxation, and trade. Roman cities across Europe and North Africa repeated this structure, creating predictable orientation. Urban space became legible. Centuries later, the Manhattan grid system, formalized in 1811, imposed a similar logic on a rapidly growing island. Streets and avenues formed a strict rectilinear pattern regardless of topography. Hills were leveled, wetlands filled. The grid prioritized efficiency and land division. Property could be measured and sold with clarity. While critics argued it ignored natural landscape, the grid created a framework flexible enough to absorb skyscrapers, parks, and dense commerce. In 19th century Paris, Baron Georges Eugene Haussmann transformed medieval streets into wide boulevards. Narrow alleys were replaced with axial avenues radiating from monuments. This redesign improved sanitation and circulation, but it also strengthened state control. Broad streets prevented barricade construction during uprisings. Urban renewal here intertwined hygiene, aesthetics, and political stability. The 20th century brought planned capitals designed almost from scratch. Brasilia, Shaped under the guidance of Oscar Niemeyer and urban planner Lucio Costa, adopted a monumental modernist layout resembling an airplane from above. Government buildings align along a central axis, separated from residential superblocks. The city expresses national ambition through abstraction. Its order is deliberate, almost sculptural. Earlier reformers had proposed different models. Ebenezer Howard's Garden City concept imagined self-contained communities surrounded by greenbelts. Housing, industry, and agriculture would coexist in balanced proportion. The goal was to alleviate overcrowded industrial cities while preserving access to nature. Though rarely realized in pure form, the idea influenced suburban planning and satellite towns. In Barcelona, Ildefons Cerda's eye-example extension introduced chamfered street corners, wide avenues, and uniform blocks. The cut corners allowed better visibility and turning radius for traffic. Cerda envisioned light and air reaching every dwelling. The grid softened at intersections, blending efficiency with humane scale. Urban planning here combined geometry with public health. Long before modern grids, ancient cities defined civic space through gathering areas. The Agora of Athens functioned as marketplace and political forum. It was an open field framed by stoas and temples, where commerce and debate coexisted. The arrangement encouraged participation. Space fostered democracy. Similarly, the Forum Romanum concentrated religious, judicial, and commercial life within a defined urban core. Temples, basilicas, and triumphal arches lined the space. Processions moved through it. Public life unfolded under architectural supervision. The Forum linked civic identity to spatial form. Not all cities relied on rigid grids. Venice developed along canals rather than streets. Its urban fabric follows waterways, with bridges replacing intersections. The Grand Canal acts as a central artery. Buildings face water rather than roads. Urban logic adapts to lagoon conditions, transforming maritime necessity into civic character. Defensive considerations shaped many historic cities. The walls of Istanbul, originally built under Theodosius II, enclosed and protected Constantinople for centuries. Multiple layers of fortification deterred invasion. Gates regulated entry. Walls defined not only defense, but boundary of identity. In contrast, the Medina of Fez evolved organically, with winding streets responding to climate and social structure. Narrow passages create shade and privacy. Neighborhoods cluster by craft and kinship. The layout resists rigid geometry, prioritizing microclimate and community over axial planning. The city of Kyoto, influenced by Chinese planning principles, adopted a grid pattern aligned with cardinal directions. The imperial palace anchored the northern center. Though later growth altered the symmetry, the initial order reflected cosmological beliefs as well as administrative clarity. Urban infrastructure also reveals structural intelligence. Cities of the Indus Valley, such as Mohenjo-Daro, incorporated advanced drainage systems beneath gridded streets. Standardized brick dimensions and covered sewers indicate organized governance. Planning extended beyond visible architecture into concealed systems. Defensive walls appear across cultures, from European fortresses to Chinese city enclosures. They serve military function, but also psychological reassurance. A wall marks a limit. Inside, order prevails. Outside, uncertainty remains. Port cities illustrate another dimension of urban logic. From ancient Mediterranean harbors to later Atlantic trade centers, docks shaped layout. Warehouses, markets, and customs houses cluster near water. Trade routes dictate growth. Urban form aligns with economic current. Across these varied examples, planning reflects more than aesthetic preference. It encodes priorities: defense, hygiene, commerce, ideology, or cosmology. Some cities impose order from above. Others evolve gradually through adaptation. Grids provide clarity. Organic networks provide resilience. Public life depends on this framework. A square invites gathering. A boulevard encourages procession. A canal supports exchange. Streets determine visibility and movement. The city becomes a stage on which collective life unfolds. Power often reveals itself through alignment. Axial avenues frame monuments. Elevated palaces oversee districts. Administrative centers occupy central positions. Planning directs attention and reinforces hierarchy. Even when subtle, spatial arrangement influences behavior. Yet no city remains static. Layers accumulate. Medieval lanes intersect with modern boulevards. Defensive walls become promenades. Industrial docks transform into cultural districts. Urban order adapts to new conditions. Cities are physical and social frameworks whose geometry shapes movement, visibility, commerce, and gathering. What looks abstract on a map becomes the daily rhythm of public life, revealing that urban space is never neutral, but always intentional. Modern cities express ambition vertically. The rise of skyscraper culture transformed urban identity, turning height into economic and symbolic capital. Towers cluster in financial districts, competing for visibility and prestige. In places like Dubai, the skyline itself becomes branding. The concentration of high-rise buildings signals global connectivity, wealth, and rapid development. In Pudong, Shanghai, farmland was transformed within decades into a forest of glass and steel. The skyline along the Huangpu River presents a curated image of technological progress. Architecture becomes announcement. Similarly, Tokyo's density model demonstrates a different strategy. Instead of singular monumental towers dominating empty space, the city layers infrastructure, housing, commerce, and transit within compact footprints. Density here is normalized rather than exceptional. Contemporary planning increasingly speaks of the smart city. Sensors monitor traffic flow, energy use, and environmental conditions in real time. Data guides decision-making. Projects like Masdar City in the United Arab Emirates attempt to combine digital monitoring with renewable energy systems, walkable layouts, and reduced car dependence. Sustainability becomes measurable through infrastructure. Urban adaptation also reclaims obsolete industrial space. The High Line in New York converted an abandoned elevated railway into a linear public park. Rather than demolish, planners repurposed. The project reshaped surrounding neighborhoods, increasing property values and foot traffic. It also sparked debate about who benefits from such transformations. Urban renewal remains contested. Revitalization can improve safety and services, yet it may displace long-standing communities. Redevelopment often changes not only buildings, but social fabric. The debate centers on equity as much as design. Cities must balance growth with continuity. Nighttime lighting has become part of urban identity. Architectural illumination outlines towers, bridges, and monuments after sunset. Carefully designed lighting enhances safety while shaping perception. Skylines glow, redefining public space beyond daylight hours. The city extends its visual presence into darkness. Commercial environments influence social behavior as well. Shopping malls create controlled climates and curated circulation paths, blending retail with leisure. Metro systems, by contrast, structure daily movement more invisibly. Underground networks determine commuting rhythms and expand urban reach. Transportation becomes spatial organizer. At the same time, informal settlements emerge where planning fails to meet housing demand. Slums and self-built informal neighborhoods grow through necessity rather than formal design. In response, social housing projects attempt to provide affordable alternatives with varying degrees of success. Landmark structures such as Beijing's CCTV headquarters, with its looped geometry, show how architecture can also symbolize media power within dense urban fabric. Across all these conditions, public space psychology remains central. Squares, parks, sidewalks, and transit hubs shape how people interact, pause, or pass through. The modern city is a layered system where height, data, movement, and human behavior continuously negotiate space. A house is more than a structure. It is a boundary between public and private life, between noise and retreat. Unlike palaces or temples, domestic architecture reveals how ordinary routines are organized. It reflects climate, social hierarchy, gender roles, technology, and changing ideas of privacy. Across centuries, the home has quietly evolved from shared shelter into layered interior world. In ancient Rome, the domus represented an urban house organized around controlled openness. From the street, the facade appeared modest, often windowless. Entry led into the atrium, a central hall with an opening in the roof known as the compluvium, allowing rainwater to fall into a shallow basin below. This arrangement brought light and ventilation inward while maintaining privacy from the street. Beyond the atrium lay the peristyle courtyard, surrounded by columns and often planted with greenery. The Roman house balanced enclosure and exposure through careful sequencing. The preserved houses of Pompeii provide detailed evidence of this arrangement. Rooms opened inward rather than outward. Wall paintings extended visual space, depicting gardens or architectural illusions. Wealthier homes included cubicula for sleeping, triclinia for dining, and dedicated spaces for household gods. Spatial organization expressed social structure. Public reception occurred near the entrance. Private family life unfolded deeper within. In Ottoman cities, the konak introduced a different domestic logic. Houses were often divided into selamlik and haremlik sections, separating male guest areas from family quarters. Upper floors projected outward with bay windows, capturing light while limiting direct visibility from the street. Courtyards offered interior outdoor space. Wood framing and overhanging roofs moderated climate. Privacy here was architectural principle. The traditional Japanese michiya, found in Kyoto, adapted to narrow urban plots. These townhouses extended deep from the street, with rooms arranged sequentially. Sliding shoshi screens allowed flexible division of space. Light filtered through paper panels rather than glass. Small interior gardens, known as suboniwa, introduced nature into confined footprints. Domestic space became fluid rather than rigid. In 19th century Britain, the terrace house reflected industrial urban expansion. Rows of nearly identical houses shared side walls, conserving space and material. Interiors followed predictable layouts: parlor at the front, kitchen at the rear, bedrooms above. Repetition created affordability. The street became continuous facade, while individuality emerged within. Across the Atlantic, the American suburban model shifted domestic architecture outward. Detached houses surrounded by lawns offered separation from dense city life. Garages became integrated into facades as car ownership expanded. The house turned inward toward family life and outward toward private yard. Zoning regulations reinforced this pattern, separating residential from commercial areas. The courtyard house plan, found in Mediterranean, Middle Eastern, and Asian contexts, demonstrates an enduring spatial idea. A central open-air court provides ventilation, light, and communal gathering space. Rooms radiate around it, shielded from external noise. This configuration creates microclimate and privacy simultaneously. The courtyard becomes the heart of domestic life. 20th century Scandinavian minimalism reinterpreted domestic comfort through simplicity. Clean lines, light wood, and pale surfaces maximize natural illumination during long winters. Ornament was reduced. Function guided form. The domestic interior became calm rather than elaborate. Furniture was often integrated with architecture, reinforcing clarity. The Japanese tatami module further demonstrates how proportion shapes living patterns. Tatami mats, traditionally standardized in size, determine room dimensions. Furniture placement aligns with modular rhythm. The body's relationship to floor seating influences spatial scale. Architecture follows measurement rooted in daily habit. Earlier European homes often centered around the fireplace. The hearth provided warmth, light, and gathering focus. Rooms radiated from this thermal core. Chimneys became vertical anchors within houses. Heating technology shaped plan organization long before central systems existed. The concept of privacy evolved gradually. In medieval Europe, single large halls accommodated multiple functions. Sleeping, eating, and socializing occurred within shared volume. Over time, partitions multiplied. Corridors emerged, separating rooms. The modern expectation of individual bedrooms reflects social change as much as architectural innovation. Windows also transformed domestic life. Early openings were small and often shuttered. With advancements in glass production, larger panes became possible. Bay windows expanded interior perception. In colder climates, double glazing improved insulation. The window shifted from defensive aperture to framed view. Heating systems evolved from open hearths to enclosed stoves, then to radiators and underfloor systems. Central heating liberated floor plans from dependence on a single fire source. Rooms could be distributed more evenly. Comfort became regulated rather than localized. The kitchen underwent profound transformation. In pre-industrial homes, cooking occurred over open flames, often within shared spaces. As fuel sources changed and plumbing developed, kitchens became specialized rooms. In the 20th century, efficiency studies influenced layout, producing the work triangle between stove, sink, and refrigerator. Domestic labor shaped architecture. Bedrooms, once shared among family members or servants, gradually became private sanctuaries. The emergence of separate sleeping quarters reflected shifting attitudes toward intimacy and individuality. The bed moved from communal hall to enclosed chamber. Architectural boundaries mirrored psychological ones. Throughout these shifts, domestic architecture responded to technology, culture, and economy. Materials changed from timber and brick to concrete and steel. Utilities, water, electricity, gas integrated into walls and floors. The house became a network of hidden systems. Yet despite technological change, certain constants remain. Light, ventilation, warmth, and enclosure continue to define domestic comfort. Proportion still influences perception. A low ceiling feels intimate. A high ceiling feels expansive. Window placement determines daily rhythm. The private house reflects aspirations as much as necessity. It expresses identity through facade and interior choice. It adapts to family size, climate, and lifestyle. Unlike monuments, houses evolve incrementally. Renovations, extensions, and interior rearrangements reveal ongoing negotiation between habit and space. From Roman atriums to suburban lawns, from Ottoman courtyards to Scandinavian interiors, the evolution of domestic architecture traces changing ideas of belonging and privacy. The home is rarely static. It absorbs new technologies and social norms while preserving older spatial memories. Domestic space is where architecture becomes personal. It frames daily rituals, sleeping, cooking, gathering, without spectacle. Its scale is measured not in grandeur, but in comfort. Over centuries, the house has shifted from collective shelter to layered private environment. Yet its core purpose endures, to create a controlled interior world within the larger city. Modern domestic design is increasingly shaped not only by structure, but by psychology. Interior space influences mood, concentration, and social interaction. The shift toward the open plan concept reflects this awareness. By removing interior walls between kitchen, dining, and living areas, designers encourage visual connection and shared activity. The absence of partitions creates flexibility, though it also reduces acoustic separation. Space becomes fluid, and boundaries become implied rather than fixed. In contrast, the tiny house movement explores intentional limitation. Compact homes, often under 40 square meters, require efficient storage and multifunctional furniture. The emphasis is on reducing material consumption and simplifying lifestyle. Smaller space alters perception. When every object must justify its presence, design becomes selective rather than accumulative. Sound has become a central concern in contemporary interiors. Acoustic design addresses how materials absorb or reflect noise. Open plans can amplify echo, while soft surfaces, textiles, wood panels, acoustic ceilings, moderate sound. In dense urban housing, acoustic insulation between units influences comfort as much as visual layout. Quiet becomes a design goal. The concept of biophilic design reconnects interiors with nature. Incorporating natural materials, indoor plants, daylight, and organic patterns reduces stress and enhances well-being. Research suggests that exposure to natural elements improves concentration and mood. Large windows, natural ventilation, and textured surfaces subtly shape emotional response. Mass production has also shaped domestic interiors. IKEA's modular systems demonstrate how standardized components allow personalization within constraints. Flat-pack furniture adapts to different room sizes while remaining affordable. Modularity reflects contemporary mobility, where homes must adjust to changing needs. Technology increasingly integrates into domestic life. Smart home systems control lighting, heating, security, and appliances through digital interfaces. Sensors regulate temperature and energy use automatically. While these systems enhance efficiency and convenience, they also reshape how occupants interact with space. Control shifts from manual adjustment to programmed response. Color psychology further influences perception. Warm tones can create intimacy, while cool tones promote calm and clarity. Neutral palettes often expand perceived space. Designers select hues not only for style, but for emotional impact. The interior becomes atmospheric through chromatic balance. Adaptive reuse has redefined urban interiors. Former industrial spaces are converted into residential lofts, preserving high ceilings, exposed brick, and structural beams. This approach embraces history rather than erasing it. The resulting industrial-style aesthetic values raw materials steel, concrete, unfinished wood, transforming structural elements into visual identity. Japanese wabi-sabi minimalism offers a quieter philosophy. It values imperfection, natural aging, and restrained simplicity. Surfaces remain understated. Space is allowed to breathe. Rather than pursuing polish, wabi-sabi accepts asymmetry and subtle texture. The atmosphere becomes contemplative. Spatial harmony traditions such as feng shui interpret layout as energetic balance. Furniture placement, circulation flow, and orientation are believed to influence well-being. Whether approached symbolically or practically, these systems highlight awareness of spatial relationships beyond pure function. Contemporary domestic life also merges work and home. The rise of remote employment has transformed spare rooms into offices. Lighting temperature now matters more, as cooler white light supports focus while warmer tones encourage relaxation. Efficient storage systems conceal clutter, preserving clarity within limited square footage. Sustainable interior materials, recycled wood, low VOC paints, responsibly sourced textiles, address environmental impact. In modern interiors, psychology, technology, and ecology converge, shaping homes that respond not only to shelter, but to mental and environmental balance. Modern interiors increasingly depend on intelligent storage systems that integrate into walls, floors, and furniture. Built-in shelving, concealed compartments, and vertical storage reduce visual clutter and preserve spatial clarity. At the same time, sustainable interior materials are reshaping construction choices. Reclaimed wood, recycled composites, cork flooring, bamboo surfaces, and low-emission finishes reduce environmental impact while maintaining durability. In this way, contemporary domestic space balances aesthetics, functionality, and ecological responsibility within a single integrated design approach. The 20th century reshaped architecture with unusual intensity. Materials evolved, cities expanded, technology accelerated, and social expectations shifted. Styles no longer changed gradually over centuries. They transformed within decades. Architecture became experimental, ideological, and increasingly global. Innovation moved from quiet refinement to visible declaration. In the 1920s and 1930s, Art Deco emerged as a language of optimism and machine-age glamour. The Chrysler Building in New York embodies this spirit. Its stainless steel crown radiates upward in layered arcs, reflecting both automotive imagery and geometric precision. Vertical lines emphasize ascent, while ornament is stylized rather than classical. Art Deco did not reject decoration. It reinterpreted it through industrial materials and streamlined forms. Height and elegance merged into a symbol of modern ambition. By contrast, brutalism embraced raw material expression. The term derives from béton brut, meaning raw concrete. In projects like Le Corbusier's Unite habitation in Marseille, exposed concrete surfaces define both structure and aesthetic. The building functions as a vertical community, incorporating apartments, internal corridors, and communal amenities. Rather than conceal construction, brutalism reveals it. Surfaces remain textured and heavy, emphasizing mass over polish. In the United States, Fallingwater, designed by Frank Lloyd Wright, redefined harmony between building and landscape. Cantilevered concrete slabs extend horizontally over a waterfall, integrating structure with environment. The house does not dominate its setting. It anchors itself within it. Wright's approach blurred boundaries between interior and exterior, anticipating later ecological sensitivity. Across the globe, the Sydney Opera House, designed by Jørn Utzon, introduced sculptural geometry to modern architecture. Its shell-like forms, derived from sections of a sphere, required advanced engineering solutions. The project's complexity demonstrated how design ambition could push structural innovation. The building is both cultural venue and urban icon, instantly recognizable through silhouette alone. In Paris, the Pompidou Center, designed by Renzo Piano and Richard Rogers, inverted conventional architectural hierarchy. Structural elements, escalators, and mechanical systems were placed on the exterior. Pipes were color-coded by function. The interior became open, flexible space. High-tech transparency replaced concealed infrastructure. The building suggested that systems could be celebrated rather than hidden. Meanwhile, in Japan, the metabolist movement, led by figures such as Kenzo Tange, proposed cities that could grow organically like living organisms. Structures were conceived as expandable modules attached to stable cores. Although few large-scale metabolist projects were realized exactly as envisioned, the idea that buildings could adapt and regenerate influenced later thinking about flexibility and urban growth. British experimental group Archigram took futurism further, proposing visionary concepts such as plug-in cities and walking cities. Though largely theoretical, their drawings imagined architecture as mobile, temporary, and technologically saturated. They treated cities as dynamic systems rather than static monuments. Architecture became speculative rather than purely constructed. By the late 20th century, deconstructivism challenged formal stability. Influenced by philosophical ideas about fragmentation, architects broke away from orthogonal grids. Angled planes and distorted geometries became expressive tools. The Guggenheim Museum in Bilbao, designed by Frank Gehry, exemplifies this approach. Its titanium-clad curves appear fluid and unpredictable, yet are supported by advanced digital modeling. The building demonstrated how computational tools could translate complex shapes into buildable structures. In contrast to expressive curvature, the Seagram building in New York, designed by Ludwig Mies van der Rohe, refined the international style. Steel and glass form a disciplined facade, set back from the street to create a public plaza. Ornament is minimal. Proportion and material clarity define presence. The international style promoted universal design principles that could be replicated across continents. Minimalism extended this reduction further. Surfaces became smooth, color palettes restrained, and details precise. Architecture aimed to remove distraction, allowing space itself to dominate perception. Light, shadow, and proportion became primary elements. In minimalist design, absence becomes expressive. At the same time, postmodernism reacted against strict modernist austerity. Architects such as Michael Graves reintroduced color, symbolism, and playful historical references. Facades incorporated exaggerated classical motifs and bold geometry. Postmodernism questioned the idea that architecture should be purely functional. It suggested that buildings could communicate humor and memory. High-tech architecture embraced visible engineering. Exposed trusses, tensile structures, and glass facades emphasized precision and transparency. Rather than conceal structural complexity, designers highlighted it. Technology became aesthetic language. Structural elements were not hidden behind walls, but displayed as compositional features. As the century progressed, attention turned toward adaptive reuse. Instead of demolishing industrial warehouses or factories, architects converted them into housing, museums, or cultural centers. This approach preserved embodied energy and historical character while accommodating contemporary needs. Adaptive reuse acknowledges that innovation does not always require new construction. It can emerge from reinterpretation. Across these movements, a pattern becomes visible. Architecture in the 20th century oscillated between reduction and expression, between rational grids and sculptural forms, between permanence and flexibility. Each movement responded to technological possibility and cultural mood. Innovation was no longer confined to material alone. It extended into ideology, representation, and digital computation. Buildings became statements about society's direction. Some celebrated industrial power. Others questioned it. Some embraced universal language. Others fragmented it deliberately. By the end of the century, architecture had absorbed steel, reinforced concrete, glass curtain walls, digital modeling, and modular experimentation. The discipline no longer followed a single dominant style. Instead, plurality became normal. Skyscrapers, museums, housing blocks, and cultural centers coexisted in varied forms. Modern innovation, then, was not a straight line, but a series of recalibrations. Each generation redefined what was possible, acceptable, or desirable. The 20th century expanded the vocabulary of design beyond recognition compared to previous eras. In these transformations, architecture became visibly modern, not only through material, but through attitude. It questioned tradition, embraced experimentation, and negotiated between structure and symbolism. The built environment became laboratory as much as shelter. From the geometric optimism of Art Deco to the raw surfaces of brutalism, from sculptural opera houses to glass corporate towers, the 20th century demonstrated that architecture could evolve as rapidly as the societies it served. Innovation became expectation rather than exception. Architecture is no longer shaped only by aesthetics or structural innovation. It is increasingly guided by environmental urgency and technological possibility. The future of design is less about style and more about systems, energy systems, ecological systems, digital systems. Buildings are becoming responsive rather than static. One of the clearest shifts is the rise of net zero buildings, designed to produce as much energy as they consume over the course of a year. Through solar panels, advanced insulation, passive ventilation, and efficient mechanical systems, these structures reduce reliance on fossil fuels. Energy performance becomes measurable and integrated into design from the earliest stages. In Milan, Bosco Vertical demonstrates how vegetation can become architectural element rather than decoration. Residential towers support hundreds of trees and thousands of plants on balconies, creating a vertical forest. The vegetation absorbs carbon dioxide, moderates temperature, and increases biodiversity within dense urban fabric. Greenery is no longer confined to ground level. Construction methods themselves are evolving. Entire 3D printed neighborhoods are being developed using robotic extrusion of concrete or composite materials. This technique reduces labor time and material waste while allowing customized forms. Walls are printed layer by layer, guided by digital models. Housing production becomes faster and potentially more affordable. Beyond Earth, research into Mars habitat design explores how humans might build in extreme environments. Concepts include inflatable modules covered with regolith for radiation protection, or structures printed from local Martian soil. Architecture here must respond to gravity differences, limited resources, and isolation. Space design extends terrestrial engineering into extraterrestrial conditions. Digital intelligence now participates in the design process. AI-assisted architecture can generate layout options, optimize structural efficiency, and simulate environmental performance. Algorithms evaluate thousands of variations faster than manual drafting ever could. Designers increasingly collaborate with computational systems rather than working alone. At the urban scale, parametric urbanism uses data-driven modeling to shape districts according to climate, traffic flow, and social interaction patterns. Instead of rigid grids, cities may adapt through algorithmic optimization. Streets, building heights, and open spaces are adjusted to improve airflow, reduce heat islands, and balance density. Rising sea levels are forcing reconsideration of coastal planning. Proposals for floating cities imagine modular platforms anchored offshore, capable of adjusting to water levels. Other strategies include amphibious housing that rises during floods and resilient waterfront barriers integrated into public space. Adaptation becomes central design challenge. When disaster strikes, speed matters. Modular disaster housing systems use prefabricated components that can be assembled quickly and transported easily. Lightweight units provide temporary shelter while infrastructure is restored. Flexibility and portability define these solutions. Environmental technology is also entering building exteriors. Experimental carbon capture systems incorporate materials that absorb or neutralize carbon dioxide from surrounding air. Photocatalytic surfaces break down pollutants under sunlight. The outer layer of a building is no longer just a protective boundary. It becomes an active environmental participant. Material innovation continues upward. Timber skyscrapers, built from cross-laminated timber panels, challenge the dominance of steel and concrete in high-rise construction. Engineered wood offers lower embodied carbon while maintaining structural strength. Wood, once limited to low-rise buildings, returns at urban scale. Transportation concepts influence architectural planning as well. Proposed Hyperloop stations imagine streamlined terminals integrated with high-speed vacuum transit systems. These speculative infrastructures require new spatial arrangements for passenger flow, safety, and connectivity. Automation is reshaping construction sites. Robotic building systems assemble components with precision, reducing labor risk and improving accuracy. Drones monitor progress, and robotic arms lay bricks or print concrete. Construction becomes increasingly mechanized. Even materials are being designed to repair themselves. Self-healing concrete, infused with bacteria or chemical agents, can seal cracks when exposed to moisture. This extends lifespan and reduces maintenance costs. Durability becomes proactive rather than reactive. Research into space architecture continues beyond Mars concepts. Lunar bases, orbital habitats, and long-term extraterrestrial settlements are being studied by architects and engineers worldwide. These environments demand closed-loop life support, radiation shielding, and psychological consideration for isolation. Architecture expands from terrestrial ground to planetary scale. The future of design suggests a discipline that blends ecology, computation, and resilience. Buildings may generate energy, filter air, adapt to climate, and even repair themselves. Cities may float, grow algorithmically, or extend beyond Earth. What remains constant is the negotiation between human need and environmental constraint. Architecture, once defined by stone and steel, now integrates data and biology. The line between building and system grows thinner. Innovation moves toward responsiveness, sustainability, and adaptability. The future does not erase the past. It builds upon it with new tools and new awareness.